Hello. Today we will be talking about our project, which is the cathode design for zinc-ion batteries through graphene-supported tungstate intercalated V₃O₇ cathodes. So without further ado, let's get started. Let's start with the significance of the problem. With cities and industries electrifying at a rate higher than ever, there is a huge increase in demand for the energy storages for these sectors, specifically the battery market. The battery market is projected to grow to over twice its size from 2024 to 2023, with secondary batteries dominating at 78.2% market share due to their rechargeability. So, how do we address that? We address that by looking at other fields that have wastes that could be used to make materials that are useful for the energy sector. For example, humanity produces around 56 million metric tons of sunflower shells every year, 20% of which goes to waste, most of which is burned to the open atmosphere, releasing gigantic amounts of carbon dioxide. However, this material can be used in the design for zinc-ion batteries, a battery system that has been getting growing interest in the energy storage sector. Why is that so? Currently, the battery system that dominates the energy sector is lithium-ion batteries. However, as successful as they may be, they still have their bottlenecks. Lithium reserves are scarce, so lithium supply chains are volatile and the price is extremely expensive. And lithium can sometimes be a fire hazard due to its design. So what do we do when the sector expands beyond the point where lithium can no longer meet our demand? To understand that, we will be looking at this slide shows different energy storage technologies that are present out there, like potential energy, thermomechanical energy, kinetic energy, chemical energy, thermal energy. Our project will be focusing on electrochemical energy, which is a compact energy storage system that has no moving parts and requires considerably less maintenance. What we'll be using for that is zinc ion. So as we have discussed, lithium has certain limitations, and zinc-ion batteries can overcome these limitations through being safe, eco-friendly, low-cost, with high theoretical capacity. We will be working on vanadium-based cathodes, as my colleagues will later present in this presentation, that have high capacity and multi-electron redox activity. And we will be addressing major challenges like the low electronic conductivity of zinc ions and the structural degradation that can be possible. And we will be highlighting the research gap and the need for optimization. Why are we using zinc ion? Zinc ion has many considerably good properties or comparable to lithium. For example, the price of zinc ion is $2.65 per kilogram compared to lithium's 163. However, it has a comparable radius to lithium at 385 picometers a hydrated ionic radius. Now my colleagues will discuss further on the scientific gap and the core idea of our work.
Thanks, Viras. So now we come to the mechanism or the chemistry of the aqueous zinc ion battery. It actually consists of two mainly parts, the cathode part and the anode part. The cathode part is where the reduction for the zinc occurs. It's like in the first equation, the zinc is with our material R V₃O₇, where R here represents GO₃W, which is graphene oxide tungsten. And in the anode part, the zinc is oxidized. So then we will have at the end the overall reaction as illustrated in equation number 3. So now when we want to discuss about the cathode, cathode firstly usually consists of the three main things: the active material, which store the charge, the binder, where it connect everything in the battery, the conductive additive, and conductive additive is the one that is moving the electrons, and the common material is carbon black. Carbon black actually is a petroleum based, which is environmental harmfully and has impacts. Also, it's expensive. So we come up with an alternative material, which is the sunflower shells. Sunflower shells is rich of carbon, so it's a good raw material as a replacement of the carbon black, and it will be converting to carbon material, activated carbon, through a thermal process.
Thank you, Mohammed. To test this idea, we designed the cathode with specific material characteristics The components are graphene oxide sheets, and in between them we have tungstate intercalated vanadium oxide in addition to sunflower shell carbon. The mass ratio of our electrode composition is 70% from the active material, 20% from the sunflower shell, and 10% from the PVDF binder. On the right side of the slide, we have an explanation of how the entire battery was assembled. Let's move to the material characterizations and electrochemical measurements, starting with the SEM micrograph, where we have 4 different magnifications between 100 micrometer until 1 micrometer. Then we have the XRD and the FTIR. On the left, we have the XRD with the most intense peak at about 21 to 22 degrees, indicating successful doping of graphene oxide and tungstate in the vanadium oxide. Additionally, we have several sharp peaks indicating the crystallinity of the material. On the right, we have the FTIR, which shows the functional groups in the material. We have a peak of a wave number at around 750, referring to the graphene oxide. And on the left side of the plot, we have smoothness, referring to the dehydration of the material. Next is the galvanostatic charging and discharging and energy discharge plots. On the left, we have the GCD, where we activated the battery for about 2 cycles. Then we measured the specific capacity, which returned about 248 mAh per gram. After 100 cycles, it dropped to 225 mAh per gram, and the testing is still going, as you will see soon in the video. Throughout the entire process, we maintained an efficiency of about 100%. On the right, we have the energy discharge plot, where we started with about 1.15, and after 100 cycles, it dropped to 0.85. Next is the electrochemical impedance spectroscopy and cyclic voltammetry. On the left is the electrochemical impedance spectroscopy, where we have the solution resistance at 18.9 ohm and the charge transfer resistance at 168 ohm and the Warburg impedance at 475 ohm. For the cyclic voltammetry, it shows the redox nature in the battery, where we have the upper peaks in the plot for oxidation in the anode and the lower peaks in the plot for the reduction in the cathode. It also shows the potential and current of those peaks. The highest anodic peak shows the current of 3.5 mA, which is higher than the current of the highest cathodic peak, whereas the second anodic peak showed a current of around 1.3 mA, which is lower than the second cathodic peak. Finally, we have the percentage contribution, where the battery can either show a diffusion or a capacitive controlled behavior. At a scan rate of 0.1 mV per second, the battery showed a diffusion controlled behavior of about 55%. When we increase the scan rate to 0.4, the battery showed a capacitive behavior, and this behavior kept increasing with the increase of the scan rate. Let's now leave you with the video recorded in the workstation where the electrochemical analysis was performed. First step is to cut each component in the appropriate size. We move then to the crimper, where we bind all components together. It will look something like this. This is the GCD machine, where we charge and discharge the battery for a number of cycles. If we show the data, we can view the performance of each cycle, where we show current and voltage.
What makes our project especially powerful is that it sits at the intersection of 3 main priorities that define the next generation engineering solutions: sustainability, performance, and cost. First, sustainability. This work gives a new value to an abundant agricultural waste stream and reduces the dependence on fossil-based conductive additives and contribute to a sustainable and safer environment. Second, performance. By using a functional carbon additives derived from biomass, we are targeting a real electrochemical role inside the battery cathodes, not just as a symbolic green ingredient, but as an engineered component. Third, cost. Low-value waste biomass offer a promising solution toward affordable battery material, especially for large-scale battery storage technologies where cost competitive is essential. Together, these 3 main pillars make our project broadly relevant, because strong research does more than solve a narrow technical problem. It connects material science, electrochemistry, environmental responsibility, and practical impact. And that is exactly what our project does. At the end, this project tells a simple but powerful story. A waste material, usually overlooked or discarded, can be reimagined as part of the future energy storage technology. From sunflower shells to conductive carbon to zinc-ion battery cathodes to cleaner and safer energy storage. This is more than a battery material study. It is a vision for how waste can become a value, and how sustainability can drive innovation, and how engineering can help build a cleaner future. Thank you all for your attention.